In this video, we'll cover the problem letter combinations of a phone number. So, as the input, you'll be given a phone number, which is really represented as a string containing a series of digits. You can see this an example here. The digits can only be in the range from 2 to 9, inclusive on both ends. So you can't have 0, 1, or anything like that. You need to return an array that contains all of the letter mappings that can be derived from these digits. And the way we're going to map from these numbers or digits to letters is based on this diagram you can see on the top left corner of the screen. So a lot of phones that are out there, on the keypad, next to each number, you'll see a set of letters. So like next to 2, you'll see A, B, C like you can see here. Maybe next to 6, you'll see M and O, and next to 9, you'll see W, X, Y, Z. So this is how we'll map from a number to a set of characters. So as an example, 2 maps to A, B, C, any of those characters it can map to. So over here next to the 2, we can go ahead and write A, B, C. Any of those characters are fine. 7 maps to P, Q, R, S. So we can write those characters over here. You can notice that every number is mapping to either 3 or 4 characters. Now, there are 3 options for what character replaces our 2 here. It can be an A, or a B, or a C. Similarly, there are 4 options for what can replace the 7 here. So, one valid option is, let's say we chose to pick the A to replace the 2, and the P to replace the 7. We would get the string A, P like this. And this happens to be the first string in our output. It's also possible that we still chose A to replace our 2, but we chose Q to replace our 7. Then we get the string AQ, which is what you can see right here. And you could have chosen AR. I won't write out the string, but it's AR, which is this right here. You could do AS, which is this string right here. Or you don't even have to choose A for the 2-digit. You could choose B, and then you have the same set of choices. So there's BP right here in the output. There's BQ, which is right here in the output. And you can imagine that this continues onwards. So in total, we have 3 options for what replaces digit 2 and 4 options for what replaces digit 7. So in total, there are going to be 12 answers in our output. But our task is not just to determine the number of valid letter combinations. We have to actually list them out like you see in the output here. All right, so you can see that we're making a series of decisions. At the 2-digit, we have to decide what character do we want to deal with. Do we want to pick an A or a B or a C? Let's, for now, say we picked a B. So that's one decision. After we've made that decision, we say, okay, we know that B is going to replace the 2-digit. Now, let's go to the 7 and determine what replaces that. And we're making another decision. We could pick P or Q or R or S. So we could get BP, we could get BQ, we could get BR, or we could get BS. Let's say we picked R. Then we get the answer of BR right here. So, the point is, when we're making a series of decisions, what we want to do in this problem is sort of pick a particular decision. So we pick B to replace the 2-digit, and then move on and think, all right, what decisions can we make now? We want to sort of fixate. We decide that we've chosen B, and we just move on and assume that B is our choice, and then explore the rest of the possibilities. And later on, we come back and say, all right, we've explored all of the possibilities where B replaces the 2-digit. Now, let's think about if C replaces the 2-digit and look at those possibilities. So we sort of go depth first in a way, right? We fixate on B, go all the way down and search as much as we can, and then we go over to a C. So we can actually model this out as a graph, and I want to show that on the right. So you can see, imagine we start with the empty string. Now, we want to process the 2, so the first digit here. There are 3 options for what we can add to our string. We can get an A, we can get a B, and we can get a C here. So you can kind of think of this as like a graph, right? We can go from the empty string to A, we can go from the empty string to B, and we can go from the empty string to C here. For each of these, we now have 4 options, because if we pick A to replace digit 2, now we go to digit 7. And now, I'm not going to draw the double quotes this time for simplicity, but there's P, Q, R, and S are valid options from A, right? Like this. And we can also make those same options for B. We can also go B, P, B, Q, B, R, and B, S, and the same thing for C gets filled in here. So what we're saying is we have a decision at each step. Right here is the 2-digit, and that gives us 3 options for our decision. For each of those options, we then go down to the 7-digit, and now we have 4 options for that decision. So let me go ahead and grab the graph that we want to access, or to use to diagram this entire set of digits for 2 and 7. All right, now here we have the full graph that we can use to diagram this out. So we start, actually, first of all, I should say there are only 3 levels to this graph. There's this level, and then this level. I know it looks like there's another level down here, but really this is just a part of this level. It kind of looks something like this. I just didn't have the space to put them all horizontally next to each other. So the initial level is just our empty string. This level right here is our 2-digit. This level right here is our 7-digit. So we start at the empty string on the top. Then when we process the 2-digit, we know that we can do A, B, or C. Actually, you know what? Let's do this in the correct order. Let's first say we start with the empty string and then we choose to do A. Then we go to the 7-digit, and the first option is to choose P. Now there are no more digits there, so we try to search down this way. There's nothing else. So AP is our first answer. Now we want to stick with A still and look at the next option, which is going to be a Q. We can search further, but there's nothing else, so AQ is another answer. The next thing is we want to keep our A. We want to try adding an R, and we get AR, which is another answer here. And similarly, we get AS, which is another answer here. Now that we've finished processing the A, now we go to the next option for a 2, which is a B. So we come here. That's not a great B. It's a little small. Then, once we have the B, we search down further. So we say, all right, come down here and try P. And you search further, but there are no more digits, so BP is your next answer. And this process continues, so you get BQ, BR, BS. You go back up to the 2-digit, and you choose the C option. And then you do CP, CQ, CR, and CS. This is how we populate the graph. So you can see, I mentioned earlier that this problem is about making a series of decisions. And this graph is modeling that series of decisions. You pick one of the options at a particular decision and go to the next decision you have to make. And pick one option, keep going down until you hit the bottom. Then you sort of jump a little bit backwards and say, well, what was a different option I could have made? And let's go all through the options I could have made. And when you exhaust the options at one level, let's say right here, then you go back up and say, all right, what's another option I could have made at the previous level? So you can see how this emulates a DFS. We're going all the way down one path, and then we go back, and down another path, and then down another path like that. And in fact, if we look at the individual paths, they actually correspond to our output. As an example, this path right here gives us the string AP, which we see right here. And we have another path, which gives us the string AQ, which is our next output, and so on. In reality, each of these nodes at the bottom level, so all these nodes here, correspond to one of our outputs. So there are 12 nodes in the bottom level, and there are 12 outputs. So, to be clear, the way we're able to understand that we should use a DFS here is that we're choosing one decision and searching down that path as far as we can. We don't want to go level by level in a breadth first way. That wouldn't make sense. Like if you went through all of A, B, and C here, that doesn't really easily help you get an answer. But instead, if you go all the way down one path and you just pick one of your decision options over and over again, then you do get to AP, which is a valid answer, and you can continue with that process. So we're going depth first because we want to make one decision at each level and go through the entire set of steps, instead of trying to search all the decisions at one level and then go to the next level, and so on. Okay, so we know we're making a series of decisions. We know a DFS is a way we can model this to pick those decisions and generate our output. Now, let's go ahead and talk about the complexity of this solution. I'm going to scroll down a little bit just so that we get some more space, and we can write our complexity here. So the first thing we're going to do, as usual, is we need to define our variables. So we're going to say V is the number of vertices in our graph, and E is going to be the number of edges in our graph. I wrote that a little bit quickly, but this says vertices up there, and this is going to be edges. So our time complexity is going to be that of a standard DFS, and our space complexity will be the same. So our time complexity is O of V plus E, our space complexity is O of V. The reason is because if we start with the time, every vertex, every node needs to be pushed onto our stack at some point in time, so that's where the V comes from. And for each node, we traverse all of its edges, which means that in total we traverse all of the edges, so we depend on E for our time complexity as well. For the space complexity, if we consider the worst case scenario, if we had a graph that looked like this, we would potentially have all of the nodes or vertices in the graph on our stack at one point in time, so we get O of V as the worst case space complexity. This complexity analysis is technically correct. It's not wrong, but it's probably not sufficient for an interview, for this question specifically. Because complexity is supposed to tell you the dependence of your algorithm on the input. But it's not really clear what V or E is from your input. So instead, our input, to be clear, is just this string here, 2, 7, or a series of digits. So let's define another variable, n, which is going to be the length of the input phone number. And let's try to express our complexity in terms of n as well. So let's start with the time complexity. We know that our complexity is V plus E, so number of nodes or vertices plus the number of edges. Let's try to think about how many nodes are going to be present in our graph. Well, if we look at our graph, we start with the empty string, and then the first digit has 3 options. 2 has 3 options, so we create 3 nodes. So right here, there are 3 options. Then at the next level, there are 4 options that come from the 7 right here. But you notice that we have to do these 4 options for each of the 3 options on the previous level. So as an example, A from level the 2 digit, that level, has 4 options because of the 7 digit. But B also has 4 options because of the 7 digit. And C also has 4 options because of the 7 digit. So you can see that on the next level, there are 3 times 4 nodes here. So what's important is we are basically multiplying the number of decision options here. You can see this on the left-hand side of the screen where we said that 2, 7 has A, B, C, and then P, Q, R, S. We said that there are 3 options here times 4 options here, which gives us a total of 12. So really, the 3 is just the size of A, B, C, and then the 4 is the size of P, Q, R, S. So what we're saying is you're basically multiplying the number of options that correspond to each one of our digits over and over again. That is really where the number of nodes in our graph is coming from. So to determine the number of nodes in our graph, really what we're saying is multiply whatever this number is, 3 or 4, for every single digit. So if all of our digits map to 3, like 3 different letters, then we'd have 3 times 3 times 3 times 3, and based on however many digits, eventually that ends. The worst case scenario is that every single digit is a 7 or a 9. Let me switch colors. Is a 7, not a great color, is a 7, hold on, is a 7 or a 9 here, because these 2 digits map to 4 different letters. So you can imagine that if all we had was 7s and 9s, we would be doing 4 times 4 times 4 times 4 up until, n. And let's scroll down a little bit. And let's be clear, 4 is the largest number of letters that any digit maps to. Everything else maps to 3. So if you get 4 times 4 times 4, and that so on times 4, and the number of digits you have here is n, that can also be expressed as 4 to the nth power. So what we can say is the number of vertices in the graph is dependent on 4 to the n, at least as in the worst case where we have 7s and 9s. So our complexity, let's get back to our complexity color. So our complexity is going to be O of 4 to the n, and there might be more, but we know that the v maps to the 4 to the n. Now, what is the e? Well, you can notice that with our particular graph, there is approximately a one-to-one mapping from vertices to edges, right? This p goes to this edge, this q maps to this edge, and so on. And you can see like that's approximately the case. The number of edges is not necessarily identical to the number of nodes, but it's approximately the same. So in our case, O of v plus e, specifically for this graph, the graph that we'll see in this problem, it's really not that meaningful. We can just treat that as O of v or O of v. So we don't have to worry too much about this here, like the v plus e. 4 to the n seems to encompass that. But one other thing that is worth mentioning is that we also need to think about the size of individual paths that we're DFSing down, right? So we DFS down this path here, and the size of this depends on n, because basically for every digit, we add one character to the length of the string. As an example, if we added another digit here and we had like 3 at the end, then we would have to have another level down here where we say, okay, after we choose a P, we can choose a D, an E, or an F, because these are the characters that 3 maps to. So we see that the length of the input digit is determining the length of these outputs here that we see, like this AS and CQ. These would get longer if the input sequence had more digits. So we also have a dependence on n there, because you see that, if we added another digit, then there's one more character in every single one of our strings. So there are 4 to the n nodes in the graph, but also when we're creating these strings at the end, that's going to be O of n, because they're basically the size of the input phone number right here. Okay, we can talk about the space complexity now, which is going to be something that is relatively similar. The first thing is we want to think about, so there are really 2 things that matter here. There is the output, like how big is the output going to be? And then there is the question of what is the maximum size of our stack at any point in time? So let's start with the maximum size of our stack. Our stack is going to be filled up by multiple nodes, like, being processed at one time. And we're only going to look at one path at a time. So like we'll look at this path and we won't contain anything more than that. And once we finish that path, then we move on to this path and we finish that and so on. And the length of any one of these paths, let's just take this one as an example, is just the number of digits we have plus 1. The reason I say plus 1 is because we have the empty string as our root node. But other than that, we're replacing the 2 with 1 digit, which is A. We're replacing the 7 with 1 digit, which is Q. So every digit we have gets replaced by exactly 1 letter. So that's going to be proportional to the size of our input phone number. So what that means is we definitely have an n in our space complexity. Now, and that's specifically considering the maximum size of our call stack at any point in time. We also want to think about the size of our output. For the same reason we discussed before, the size of our output is going to be 4 to the n. Because the size of our output here is 3 times 4. But you can imagine in the worst case scenario, we have all 7s and 9s. It's just going to be 4 times 4 times 4 times 4 for however many characters we have. Now, there is one point I want to make about the space complexity here. I've seen differing opinions on how people factor in your output memory in the space complexity. So in this case, the memory of this array, whether or not that counts towards your space complexity is what I'm talking about. Some people say that you cannot optimize for that output space complexity because it's always there. It's part of your algorithm functioning. So those people don't want to choose not to include your output as a part of your space complexity. Other people say, well, it's still even if that output is like cannot be changed, like you can't reduce the space complexity to optimize, it is still part of your algorithm. It still is using that much space. So other people seem to include it when they're doing their space complexity calculations. What I've found is that in interviews, it doesn't seem to matter that much like which approach you take. Interviewers seem to care more about seeing that you understand space complexity and can intelligently analyze and talk about it. So what I usually do is I'll just do what I did now. I'll say, okay, if we look at the maximum size of our stack, we see that we have an O of n complexity. If we choose to care about the size of our output, then we have O of 4 to the n times n space complexity. But if we don't factor in the size of our output, then it's just O of n space complexity. This seems to be fine in interviews. I wouldn't stress too much about this. It really just seems like as long as you showcase your understanding, you should be okay. But this is an important point I wanted to mention because some people might get confused about whether or not they should be including the output in their space complexity. All right, that's all for the approach. So let's go ahead and switch over to the implementation. Now, let's see an example of how to solve this question in JavaScript. To get us started, I've copied our example input, which is just 27, and I've defined our function here that just takes a phone number, and we have a simple test here where we run our function on the example input of 27. I also created this object here that's just going to map from numbers to all of the letters that that number corresponds to, just so that things are a little bit faster. I didn't think it was worth it for you to see me typing all that out. All right. To get us started, I want to handle a quick edge case, which is just what if the input string is empty, because that's a little bit weird. We want to return an empty array in that case. And our code wouldn't necessarily do that. I'll show that in a second. Okay, now we know what we want to do is generate all of our combinations and then return that array. So let's create that array, just called all combinations, and let's make sure we're returning it in the end. Now, we want to execute our DFS. So we want to use a stack, and we know that we can just use a normal JavaScript array. We can use our standard, the standard stuff that we see. We know that we want to, say while our stack has elements in it, pull out a node from the stack, process that node, and then add everything to the stack. Actually, before we do that, we should also make sure our stack actually has something. So we can start by doing stack.push an empty string here. Or we could just put the empty string like this. It doesn't really matter. It does the same thing. Okay. So now what we want to do is we want to say current string is going to be stack.pop. So it's just going to say grab the last element off the stack. Now we want to process the node, and then we want to add its neighbors. Let's go ahead and add the neighbors first, just because. Actually, no, never mind. We're going to process the node first in this case. So at each node, what do we want to do? Well, the goal of this question is to generate a full letter combination. So like when we have, A, P, that is a full letter combination. But when all we have so far is A, that is not a full letter combination. So what we want to do is see if the length of the current string is long enough, because it should match the length of the input phone number. If it is, then we know we have our full, everything we need, right? To generate one particular output, one of the combinations. If it's shorter than that, then we need to keep adding characters. So the way we can check this is we'll say if the current string's length is equal to phone number.length, then we want to do what? Well, we want to add it to our combinations. We can do all combinations.push, the current string, and we want to continue to the next iteration. That's sort of the process node step. Now, what we also need to do is say, okay, the alternative scenario is where there are still digits to add. So we don't enter this if condition, meaning we only have, in our example, let's just say A, and we have to pick between P, Q, R, S. What we want to do is, first of all, we have to figure out that P, Q, R, S are our options. And the way we do that is we look at the 7. But, in our code, we don't have any easy way to say, here's the next digit. So let's start by figuring out how do we get the current digit. So let's say our current string is equal to A right now. We want to know that 7 is the next digit. So what we can do is we can say the index of the next digit, so next digit index, is going to be what? Well, the next digit index here is 1, right? 2 is index 0, and 1 is right here. And right here, our string's length is 1, so it's actually going to be the same thing. It's just current string dot length. The reason is because we have, like, if we have one character here, that means we want to go ahead and jump and skip past one character here, because we've already handled that, and we want to go to the next position. So since indices are 0 based, we can just go ahead and use the string length as our next digit index. You know, you could not make another variable here. I think it's more readable though, because it's not intuitive that this is going to be the next digit index. But if you write it in its own variable, I think it's very difficult to miss that. It's a little bit more readable, in my opinion. Okay, so this is telling us the index of 7 within our input phone number, but let's go ahead and actually grab the 7. So we can say next digit is just going to be phone number at next digit index. Now we want to know, okay, what are the characters that 7 maps to? So we can say potential next characters is going to be, we're going to use our mapping up here. So number to letters map, and we're going to pass in the key, which is just next digit. So it's saying user mapping and pass in 7, which is the next digit. And we can go ahead and get rid of this now. Actually, not yet. So to be clear, this is going to be an array that looks like P, Q, R, S. I'm not putting the quotes every time, but you can imagine they were there every time. And now all we want to do is just add each of these to what we already have, which is A. So we want to do AP, put that onto our stack. AQ, put that onto our stack. AR, put that onto our stack. AS, put that onto our stack. So we can say, iterate over our potential next characters. So dot for each potential next character, and what do we want to do for each of those characters? So for P, for Q, for R, and for S. Well, we want to say push something onto our stack, which is going to be a new string. I'll go ahead and just say, let's say string with new character is going to be, and you want to copy everything you already have. You don't want to lose the A. So we'll do current string, and then we want to add our current new character, which is going to be P, Q, R, or S. So we'll say, go ahead and add this here. Then what we'll do is we'll say, all right, push the string with this new character. You don't have to put this in a variable. You could have just put this inside of the push. I just prefer to put it into another variable. So to be clear, the way this algorithm is going to work is, we have the boilerplate here, which is just like pull out whatever node. But we're going to look at the length of the current string. If it has as many letters as our phone number has digits, that means we're done with this particular string. We can push it into our all combinations array, which is our output array, because it is full. We've replaced every single digit with exactly one character. If it's less than that, then we need to add more characters to it. So what we're going to do is figure out, first of all, let's find the index of the next digit, like the 7. We haven't added any letters for 7. Let's find the index of the 7. Then we actually grab the digit itself, so we grab the 7. Then you need to say, all right, what characters does 7 map to? So that's what we're doing on line 35. And finally, once you have that array of characters, you're just going to say, for all of those characters, let's do our current string plus that character and push that onto the stack so that we can continue processing. We push them onto the stack because we don't really know. This might not be long enough. If we had 5 digits, then we can do PQ for our 2 and 7, but we're not done. So that's why we're pushing them onto the stack so we can continue processing them. Okay, I believe that should be everything. So let's go ahead and run this and see what output we get. Remember, based on the approach, we saw that we want something that's like AP, AQ, AR, AS, and then the same thing for B and C. I will point out that we're not going to get the same order of our output, but we should get the same output. So let's come over here and see what we get. Okay, so we are getting it backwards. AP, AQ, AR, AS, BP, BQ, BR, BS, CP, CQ, CR, CS. Okay, so it looks like we are getting the right output. It is backwards just because the way our DFS works. Let me see if I can show you that real quick. So let's say our stack starts off with the empty string, which it does. Then we pop it off, we get the empty string. We say, is that equal to our input length? Input is just 27. No, it's not. So we get down here. The next digit index is the current string's length. So that's just empty string's length, so 0. The next digit is going to be phone number at 0, so 2. And then the potential next characters is ABC, which is what 2 maps to. So we're going to say, oh, this should be popped off our stack. So we're going to say, add onto our stack empty string plus A, empty string plus B, empty string plus C. So we have A, B, C here. Now we go to the next iteration and then we pop. So what's important is C is what we pop because it's at the end and we start processing C. So that's the reason that you see that everything is reversed. Because in our example, when we were talking about it, we said, okay, let's pick A, which is totally fine. But in our algorithm, it's just choosing to select the last element first. So it's choosing C and searching down that path. And it's going to C, and then there's PQRS, so it goes CS, and then CQ, no, CS, CR, CQ, CP. And that should be right. CS, CR, CQ, CP, yeah. It is totally fine. It's not like incorrect, because all we care about is what elements are in the output array. We don't care about the order for this question. So I just wanted to point that out, that it is going to be in a different order. One other thing that's worth noting is that strings in JavaScript are immutable, which means that you cannot change them. You can't just add a character to the end of a string. When you do, like a string plus equals another string, really what happens is JavaScript copies, like it creates a new string, copies all of the characters from the original string plus the new stuff you want to add in your new string. That's not the most efficient. So the best way to solve this question is probably not by just adding your strings like this. Instead, what you can do is you can have an array that just contains characters so that you can push onto the array very easily. You can do that in constant time without copying the entire thing. But I would say for most interviews, it usually seems to be fine if you just copy the strings themselves, because interviewers want to get a sense for your problem-solving ability, and sometimes it's just a lot. You get into nitty-gritty details if you're doing the array method, and that detracts from the question. So my experience has been that usually I can get away with saying, here I'm going to go ahead and add the strings, and then like you say to the interviewer, I want to acknowledge this is not the best way to do it. If we're going for 100% optimal efficiency, we should probably use an array and just push onto the array and then join it into a string at the end. And you can just ask the interviewer, is that something, like, do you want me to refactor to use that method? And you can just see what they say. If they really care about it, then you should probably do it. If they're like, nah, I care about the BFS, the DFS here, then don't really worry about it too much. Okay, so those are just 2 little points I wanted to make about the solution. But the core idea here is the DFS that we just walked through. So that's all for this video, and I'll see you in the next one.